Okay, guys, today I'm going to go through question 2 just in general and we can practice them then. So the first thing, so question 2, I'll try and get through the whole lot, but I'll see maybe A and B might just do it and then I'll do C in a different video because it could take us a while to get through it. So part A is always your destructive testing, okay? So your destructive, so you need to know your 2 hardness tests, Vickers. I'm going to go through these now in a second. Burnell. And the other one you have is your impact, which is your IZOD, IZOD, and your Charpy. So this is for part A. Another thing you need to know about it is so the different terms. So again, you have like metal fatigue, metal creep is one. So again, that's where the metal stretches over time. And then you have metal fatigue is also over time, but it's to do with an on-off sort of stress. So metal creep is where like you have a soft material like lead or copper or something is under huge continuous stress and it just stretches over time, whereas fatigue is where you have something strong like steel is under maybe stress, it's on off, and then eventually it cracks and shatters. Okay, so again that happens over both of them over a long period of time. So those are a few key things you need to know. Also need to know advantages and disadvantages for both of these. Okay, so I'll start off with my Vickers. So again, they could ask you to choose, if they ask you to decide on a test to check the hardness of material, again, Vickers or Burnell. So my Vickers like a V, so my thing looks like it's in what you call an upside down pyramid. Like that, okay? Looks like an upside down pyramid like that. So it's Vickers. Again, so you need to talk about what the indent leaves. So the indent, when it goes into a piece, it leaves like a square. Like that. How it's measured is you measure the diagonals. Okay, so you join the diagonals together, measure the distance, and again, so the further, so again, the bigger this distance is, the softer it is. Same goes for Burnell. The bigger the circle is, the softer the material is. Okay, so Vickers, so again, you could draw something like those people that are pushing for A's and things like that. You could be drawing something like this. Again, this is just the machine. Very, very rough. I'd be expecting better drawings than this now. And then look something like that. That's your Vickers machine. Again, the piece put in there, this puts into it, and that tests the hardness. So again, hardness is to do with so the hardness of material is how it's able to withstand being dented or indented. So like glass and even acrylic are hard materials, brass as well, quite hard materials. So again, Vickers, again you talk about, so again, it's suitable for, it's not suitable, it's quite universal compared to Burnell. Very soft materials are no good because that will just get lodged in it, because that's actually quite small. That'd only be like the tip of a thumbtack, like it'd be tiny, like. So again, if it's very, very soft, it'll go into it and get lodged in it, and that's really sort of what just trying to think, is there anything else we need to mention for Vickers? Not really. So you just talk about, so again, the shape of it, how it's measured, advantages, disadvantages. Again, I've just mentioned the hardness of the material, and that's really all you need to talk about. Again, so you just talk about the hardness is it's able to withstand indents. Okay, so go for Burnell, B for Burnell, B for ball. So again, Burnell is not great compared to Burnell isn't great, it's just a sphere. Ball leaves an indent that looks like a circle, so I'm going to just draw a little circle on this to make it look like a sphere. What they do is you measure the diameter. Again, bigger this is, softer it is. Your advantages, so again, it's quite a simple test. So again, you could actually do this in the Vice at home. You could do this in the Vice in the workshop, but again, you wouldn't get a reading. But another simple test. Another thing is they have different types of, but there's different sizes of spheres, so you have different. And bad thing about it is if the metal is too thin, it can distort the ball into like an egg shape. So it can't do materials that are too thin or too soft. because the ball will get lodged in it. Okay, so again, same thing as I drew before. Then I'm just going to draw and then that looks like a sphere like that. This thing comes up, and that is Brinell. So again, you just have your Brinell. So again, few key things you need to mention: advantages, disadvantages, how it's measured, the shape of the thing, and again, so we're just talking about what it does. So again, it checks to see the indent. It's used to check the hardness of the material, see how far the material can indent. Okay, again, if material is extremely hard, this thing will also distort. So again, it's just like sort of if you had a balloon and squashing it, it changes shape. Again, so that's why it's just not as reliable as a Vickers. Okay, so there are your two hardness tests. The next one you have, okay, I went through Charpy and IZOD yesterday, but I'll go through them again really quickly. IZOD, so I straight away, I know the piece is standing up. Not going to put an indent in it yet. Just going to draw it like this. IZOD, O1, so it's clamped on one side. What it means by one side is this side here is clamped, not this side, so understand. Okay, so it's clamped on one side. Each one of them has a striker, something like this, anything at all really. It's coming down 0 for 167 joules is the force that it's coming down at. Again, so we need to think about where does the notch belong. So again, if we put the notch this side, it's going to do very, very little. If you put the notch this side, it'll help it along. It'll help it break. Again, we want it to break at a certain point. So again, that's your 167 joules. Again, key things, a few things we've shown visually, but you just should jot them down. So again, it's held vertically, clamped to one side, so notch, O-N-O-T-C-H, facing striker. And I've mentioned 167 joules there. Okay, again, those people pushing phrase, again, you'll actually draw the machine. I actually have the machine here, one sec. So you will draw something that looks like that. So again, that's your striker there. So the striker, that's for both the IZOD and the Charpy. So again, you can see I don't know if you can see the mouse there. You can see the pendulum's held up. Again, the higher it's held up, the more joules you get, the more energy you get by the time it strikes it. Again, how is it measured? Let me get rid of this one sec. How is it measured? So it's measured. So we have our striker travels after impact. So again, this is a toughness test. What toughness is the material's ability to withstand sudden impact. Okay, so again, the likes of crash barriers, anything like the chassis of cars, these will have to be impact tested. Okay, so that's IZOD. So again, held vertically, clamped on one side, notch facing the striker. Again, it's measured by the striker, how far the striker travels after impact. And then again, if you're pushing for full marks in this question, you want to be drawing something like that. Again, very, very little last week spoke about that there though. Okay. The next one is Charpy. So CH. H horizontal. So another piece looks something like this. I'm not even going to draw the notch yet. There we go, piece is held horizontal. So Charpy, again, think about it, if it's held horizontal, if you can imagine if I was holding this out like this, clamped to one side, and I hit it again, it's just going to move. So it needs to be clamped on two sides. So I'm just going to clamp it again. It's not really clamped, it's just sort of held on two sides, just sits on a ledge really. Oh, such a bad drawing. It's not too bad. There we go, so clamped on two sides, so clamped. Clamped on two sides, so it's held horizontal. Held horizontal, clamped on two sides. Again, we need to think about the striker. Oh, sugar, didn't leave much space for the striker. The striker's coming down like this, we'll say. It's coming down at 300 joules, so more or less than Charpy. Again, there's more energy coming down, so again, it's coming from a higher angle, so instead of coming down from a lower angle, if it comes up, it has more energy by the time it contacts it. Okay, so again, same thing, measured by how far, as we said here, it's measured by how far the striker travels after impact. So again, the striker's coming down here like this. Again, the notch on this in this instance is away from the striker. Notch away from the striker, it's held horizontal, clamped to two sides, and then the jewels. Jewels probably the most important thing, a lot of things that people continuously leave out. Is there anything else I need to mention there? No, same again, it's a toughness test. Now there are your 4 toughness tests that can come up. The next thing I want to look at is a graph. Okay, so I might just look at the graph from the mock. Where's the mock? Oh, so there's the graph from the mock. So again, it's a stress strain graph. 45, you can see the top, it says 45, 90, the whole way up to 340. So I know on the left has to go up to 340, and then on the bottom needs to go up to 8, we'll say. Okay, so I'll leave this here somewhere that I can read it. Okay, so when I do this without oil of ruler here, 340, so I might go up in 50s. 750s makes 350. Okay, so I need to divide this by 7. So it's 16. Okay, so every 2. Don't worry if you go over, it'll be alright. So that's up in 7s. And then the next thing I have, I'm going to go over, this needs to go up to 8. So again, I can go up in 2s as well. Vital that these are all equal, or else you're going to end up with a not so great graph. Okay, so the graph's like that. So again, I said I need to go up in 50s here. So 50, 100, 150, 200, 250, 300, 350. And I have 1 extra to spare. Then along here, 1, 2, 3, 4, 5, 6, 7, 8. Where I got those numbers from, again, as I said before, the top always shoots up to the left. Okay, so top always goes up to the left. So what you have there then, guys, so I have the first point we're going to look at is 45, 0.5. So I have to go to, so it's 45 up to 45, which will be somewhere there, just below 50. 0.5 halfway, there's my first point there. I'm going to do this in marker so it's easier to see. Okay, so that's where my numbers came from. I went up to 350 here, because it goes to 340 there, and again the top goes up to the left. And 7.5, there's no point going up in 0.5s or anything like that, go up in 1s, makes it handier for you. The next one is 91, so I'm going to go here and go up to 90, so 90 somewhere there. Again, in the exam you wouldn't want to be drawing big dots here like this, so again you always start off, you wouldn't want to be drawing big dots because it shows it's a sign of inaccuracy. Next one, 135, 1.5, so 135, we'll say there's 125 halfway, 135 somewhere there. So far we're going up in a straight line, which is good. 200, 2.25, so 200 is easy enough. 2.25, so that'll be 2.5 there. Half that again. Okay, so the 2.25, draw a dot, like that. Okay. 2.25, 275, 3.25. I'm just going to keep going. So there's 2.75, 3.25. So there's 3.25 there. 4 up to 4 and 308. So just above 3. Should start to curve off now. So you have your straight line, and then it should start to curve off. What we have 5 goes up to 5 here goes up to 3.35, so we can sort of halfway. Yeah, it's trying to curve off now. 6.5 up to 3.45, yeah. And then 7.5 up to 340, so again, just there. That's it now. I've probably gone a bit above, but it's alright again. I don't have graph paper to help me. So again, and then all you have to do is just join the nice smooth curve. Try and do it as smooth as you can. And there we go. That's what you call a stress strain graph, okay? Stress strain graph, bit different to a load extension graph. Now the two things that's asking us is we need to calculate the Young's modulus. Okay, so the Young's modulus is Young's modulus stress over strain. Young's modulus stress over strain, so stress over strain, so you could just go to the graph, so go to 2, up hit here, go across and take the figure here. This side down here is strain. This is stress. Stress is to do with the amount of pressure it's under. Strain is the amount it extends. So I'm just going to take stress from here. So 45 over 0.5. So it's 45 over 0.5. I remember from yesterday that's 90, and the units is kilonewtons per millimeter squared, I believe. Okay. The next thing then you have is your determine 0.1% proof stress. So what the proof stress is, that's why the pick is 0.1%. They want to see at what stress level. So again, we're at what stress, because again it doesn't move. So again, this shows our extension. We're just going to come over to 1, up to here, hit here, and then that will show us where this thing starts to distort. So where it starts to be permanently damaged. So we go to 1, you go parallel to the graph, hit the graph, go straight across. And you can see there, I'm not too far off. That should be roughly 325. And then you're wondering, where do I get my units? There's my unit right there, because that's where stress is measured. So it's 325 newtons per millimeter squared. Okay, and that is that question done. Full answers always, the graph always worth 10 marks, and then you probably would have got a 4 and 4 for each of the 2 questions. I'll keep going with the rest of it. Actually, I'll look at a load extension graph. Do I have one here to go? If I get looking at a load extension graph, it'll be mighty, and then I might just leave it at that for this video. Let's see. Okay, so this is load extension. Question 2, always load extension. Here we go. There's load extension graph right there. Okay, so they've given us, again, straight away, this question here, they've given us a few dimensions. So again, this is the diameter is this, the gauge length is this. You're going to have to use them. Simple as. Okay, so load extension, and they're looking for the ultimate tensile strength, and they're looking for 0.1% proof stress. This is a bit trickier, this one again. Stress strain was nice and handy. Load extension, bit trickier, not too bad though. Okay, so we'll start that again. So we can see there that the top goes up to 96, or sorry, even 108, and the bottom goes to 1.4. Okay, so we can see that this is quite, again, the amount of load needed is actually very, very small, but the amount of extension is very, very small. So this is quite a brittle, yet a weak material, so you'd imagine the likes. It says non-ferrous alloy, so I'd say maybe would it be something like, probably like magnesium or something like that, something that's very, very, it's not hectic, it's quite a brittle material, but not that strong. Again, it's very strong when it's mixed with aluminium though. Okay, so we'll do this one and that'll finish up this video. Okay, so this is our load extension. Well, actually, I'm about to draw the graph first. I could be left high and dry and not enough space to do it, so we're going to draw this. So obviously, we're doing this on graph paper in the exam, make it handier for yourself. Oop. Okay, so something like that. So again, we know, sorry, I said it goes up to 108, so we'll knock it off. 120, we'll go up in 2s. Yeah, so we'll go up into 2s, we'll go up in 20s. So 6 notches. Along the bottom goes up to 1.4. I'll go up in 0.2s maybe, or I could go up to 5. And, yeah, go up in 0.2s. Okay, so I need 6 notches along the left, and then 7 along the bottom. 1, 2, 3, 4, 5, 6, perfect. And then 7 along here. Again, very important that all these are equal distance. Again, this question, don't go doing first notch is 15, second notch is 25, third notch is 40. Don't, because it's just not going to work. So just look at the highest number, and that's where you start off. What I said was going up in 20s. 20, 40, 60, 80, 100, 120. That does as well. And then along the bottom, I said I was going to point to, also 0.2, 0.4, 0.6, 0.8, 1.2, 1.4. So again, I know my last one is going to finish there. Yeah. Okay, so the first one is quite tricky. 15, 0.06. Okay, so 15, so 0. So there's 0.1, so 0.06 somewhere there. 15, 0.06 somewhere there. Again, with graph paper, you're able to get this much more approximate. Then 0.1, which would be there, and it goes as far as 25. So 25 somewhere there. Then I go 0.16, which is somewhere there, and that goes up to 40. Okay, that's nice and handy. It's on a whole number. So again, Don't be using big blotches when it comes to things. So again, how I'm doing this again, so you have it, the next one, so I've done, so on 60, 0.26. So what I do is I go, 60 is on top, so I go up to 60, go over to 0.26. So up to 60, over to, there's 0.26, there's 0.3, there's 0.26, somewhere there. And I go up, I'm leaving another mark. So again, both graphs, you should have a bit of a straight line for a bit, and then it should sort of ease off. 80, 0.38, so that's just below 4. 80, and then 100, 65, that's 7, 65 is there, 100, 65, now it should start to ease off. 107 is somewhere, there's 110, so 107 somewhere there. 107 is 0.9, so 0.9 is there halfway. 1 up to 0.8, so it's basically on the same level. And then 1.2 is just coming down slightly because it's gone to 1.105, and then we go to 96, which should be somewhere here, and 1.4. There's our graph. Okay. In theory, the graph. Okay, so that's all the data we were given. Okay, so that's the graph. So again, you can see this here, the straight line. They could ask you to label it. That's your elastic limit. Then you have here, that's your start of necking. So again, your necking is where the material starts to bend and starts to break. So again, where's this picture here? Is that it there? So again, you can see there's the necking there. So again, you have two different types of breaks. You have a brittle break where it's just a shear break, and then you have a ductile break where it necks, and then you have a cup and cone. Okay, so that's so again, you can see in the ductile break, you can see the necking very, very vividly. Okay, so cup and cone, again, so brittle fracture, so it means the two of them just shear again, very, very little extension on it, just shatters or just cracks straight down the middle. Acrylic cast iron and glass, and then the other ones again leaves cup and cone, so aluminium and steels. Aluminium very much so leaves a cup and cone. It's very, very soft. That's our graph done. Next thing it's looking for is ultimate tensile strength. Okay, so for the ultimate tensile strength, we have to do a bit of calculating. Not too much though. I have a picture here that talks us through it. So what we need to do here, that's our ultimate tensile strength. So what I need to do is I need to get my peak load, which is at the top. I need to do my cross-sectional area, which is pi r squared, and then I need to put one over the other. Okay, so pi r squared, that is your cross-sectional area. Okay, so I want to find the piece. So again, the tensile piece, if I go back to this, I want to find the... No, geez, okay, one is over the other. I want to find the diameter of that. I want to find the surface area of this piece here. Okay? I'll hide that back again. So pi r squared. So again, it says in the diagram, pi r, all I need is r. Diameter is 10, so again that means that the radius is going to be 5, so it's pi r squared, so 25, so r squared 5 is 25 by pi. For the sake of argument, we'll just say 75. It's actually 78 millimeters squared. That's one answer. Okay, so let's see, was this the right image? No, this is here, isn't it? Okay, so a cross-section area, and then I need to get my highest load value. So what I do is I go to the peak of the... Again, I can take that from the graph. I can look at the graph and just look for the highest one, which is 108. So I know that it's 108. Or I could just go to look for the top of the graph, go over here, and that should be 108 over there. Okay, so I put 108 over 78. I'd hardly be lucky enough in that. The drawing I used is... No. Just need to do it so again. Let me just get this on the calculator. 108, so it should be 1.2 something. So 108 divided by 78, 1.38. So it's 1 is equal to 1.38 kilonewtons per millimeter squared. I'm pretty sure that's it, isn't it? Yeah. Okay, so that's our unit. So again, that's our proof. That's our not proof stress. That's our tensile strength. So again, we need to take the peak, put it over the cross-sectional area, and that's us done. Now, proof stress on the other hand, that's the next question. The last part of this question, proof stress. Okay, so again, it's asked us for 0.1% proof stress. 0.1% proof stress is as I said, it's the stress that the material needs to take before it starts to bend or distort or stretch. Okay, so I have a picture here. Bear with me 1 second. So there's our proof stress. So again, 0.1. So again, we were given a gauge length. Our gauge length is 50 millimeters. So I'm going to do this on a different sheet because I'm running out of space here. Hold on to that though. Where's my sheet? So you have to think about. So you want 0.1%. 1% of something is something divided by 100. So it's equal to dividing by 100. 0.1% is also, you put another 0 onto it, so it's dividing by 1000. Okay? So the gauge length I'm looking at, is here. I'll put the thing back up in a second. Gauge length, I set 50. So gauge length is 50 millimeters. And then all we need to do then is put we've already got our cross-sectional area on. Jeez, will you hide? There we go. 0.1% is divided by 1000, 1% is divided by 100. So we need to divide 50 divided by 1000. It's equal to, so again, you put be 0.0, 1, 2, 3, 5. There we go, 0.05. So that's where we go from. So you divide by 1000, and that's where you're going to go from in this drawing. So we go from 0.05, which will be somewhere here. Oh my god, what a mess of stuff here. 0.05 parallel up till we hit the curve. Hit it. Straight across. Looks to be about 90, say 95 for the sake of argument. So that's what we call our proof load. So the proof load is 95. And then if you're ever stuck with the units, just look back at the thing. So again, you can see the load is measured in kilonewtons. It says it on the drawing. So it's kilonewtons. And then it's, as you can see from our drawing here, it's proof load over cross-sectional area. So it's proof load, which is 95 kilonewtons over a cross-sectional area. I have it from here. It's there, 78 millimeters. Okay, it's squared even. So again, I know our answer is going to be in kilonewtons over millimeter squared. Phone out again, have a look and see if this is 95 divided by 78. So 95 divided by 78 gives me 1.217. So that's 1.217. Again, I might say just bring it to nearest decimal place. That would be 1.218. Okay, and that is your questions there. Okay, so I'm just going to go through one last thing that I went through yesterday. What are we doing at? Oh, geez, nearly half an hour. My God, sick of listening to me. Again, you have 3 different graphs here. One is like this, one goes up like that, and the other goes up and breaks. Again, this one here is a soft material, not tough, so copper is very, very ideal for that. This one is your mild steel. It's flexible, it's ductile, but it's also very strong. This one here is strong, but it's brittle, so it's something like brass or cast iron or mainly a high carbon steel. Okay, so again, they could ask you to analyze different graphs, things like that. That came up last year. Don't fancy it to come up again, but it's simple, just get you to make one. Okay, so that's part A and part B of question 2, just things that you need to look out for. Okay, thanks guys. I'll bring part C later on.